right, so the last time we were talking about splitting fields, and I left you with the following example. So a splitting field, um, so if you have a polynomial here, so it's got the roots here. A splitting field for f of x over f is so it's the smallest field that contains f, and such that polynomial splits down into linear factors, right? So for example, then f prime is everybody's favorite field we looked at before. I believe that was the last example that we built. Here is a theorem. If two if K is a field and f of x is a polynomial in this field, and say, we'll say the degree of f of x is equal to n, which is at least one, then there's a splitting field f of x over k such that if I want to guess what this is, right, it's a good guess, but it's actually be much bigger in factorial. Oh, right. And so, so here, I'll prove this formally, but here's sort of what can happen. So suppose I walk up to you on the street, you get 35 polynomial, right? And I say, okay, find me a splitting field. Well, what do you got to do? You got to dump all 5 of those roots into your base field, right? So what do? You first take a root of that degree 5 polynomial. Now you're up to a degree 5 extension. What happens to your polynomial? Well, your polynomial, because it's stuck on this root, it's now got a root. But it might factor into a linear to the chordic, and that chordic may be stuck. So what do you got to do to get the rest of the roots? Well, now you got to throw in a root of the chordic, and that's another jump of at most 4, right? And then you might have 2 linear factors in a cubic, so you might have to go the full 9 on this one. 9 in this case being factorial, which unfortunately is another factorial. So proof. Proceed by induction on n the degree of f. And well, if n equals 1, then f of x is linear, and f equals k, and the degree of f over k equals k over k, which is 1 with 1 factorial. And so the linear case is no problem. right. We now assume that if, uh, F has degree n-1, then there's a splitting field for F. For F over K. Of 3 less than or equal to n-1 factorial, right? And this is just sort of like the informal argument that I just gave you all. So now, suppose that that the degree of f of x equals n. Now let G be an irreducible factor of degree more than 1. Of f degree more than 1. Why more than 1? Well, notice if all irreducible factors of f of x have degree 1, well, that means that f of x splits into linear factors already, right? And so we're done here. So let u be a root of g of x. Remember, g of x is this irreducible, it's an irreducible factor of f of x of degree more than 1. Then there's extension of, well, let me say, extension ku of k such that k u k is equal to q of x, which is bigger than 1. And in fact, explicitly, we've constructed ku ku is actually formally is the polynomial ring over k modded out by that the ideal generated by g of x, which is prime, and so that gives you actually a field because kx is PID. So in ku, So now we take our polynomial f, which was originally a degree n, and we factor it in ku. I don't know much, but I know that it's got at least that, it's at least got a factor of x minus u. It might have more linear factors, but I don't care about them. I'll just put them all together with whatever I call h of x. And h of x, where does this live? Well, its coefficients come from ku now, right? Because I've got this u here, so the coefficients there have to come from ku, x, and degree of h of x is equal to n minus one. Because the degree of f of x is equal to 1 and x minus u is linear. And so by induction, there's a splitting field of h that contains k of u. There exists a splitting field of h of x over ku. And I guess I'll call this something. Such that the degree of f over ku is less than or equal to n minus 1 factorial. Notice that f of x splits in f because f of x is a linear times h of x, and h of x splits in f. So f of x must split in f. And the degree of k is equal to the degree of f over ku times ku over k, which is less than or equal to n factorial, and this is n, right? Well, this is, I'm going to be a little bit more explicit. This is degree of p, isn't it? Right, which is less than or equal to. Okay, any questions? Okay, so this brings me to a definition here.
How could we use the induction hypothesis on K even though we assumed it for K? Is it because we assumed
That will be assumed for all fields.
Okay, yeah.
Okay, so right. So let me give you the following definition. We say that f is a normal extension of the field K. It's contained some larger field F. We say F is a normal extension of K, or F is normal over K if every polynomial that's irreducible in KX, not constant. If every f of x in KX, of degree greater than or equal to 1, constant, I don't want to be zero polynomial, that has a root in f, actually splits in half. Okay, so what does it mean to be normal? It means that if you've got a polynomial that can't be broken down in KX, if f is a normal extension, if you've got one root, we've got them all, right? This is kind of surprising that this would happen, but actually it's fairly common. Can anybody give an example of, okay, anybody give an example of a normal extension?
C normal over R.
Right, well, I was gonna be smart enough and say K is normal over K, right? I mean, so that's kind of a ding dong kind of answer. But yes, C is normal over R, because, and that's the old thing that we've known from folklore days, right? If you have a root, or if you have a polynomial over R, if it's got a root, then it has to have its complex conjugate root, right? And so you can sort of use that, yes.
Q with an n square root of n of 1.
And if you look at Q, where B is normal over Q. Right? Because, let's suppose that you have, let's say the A and B are. Let's say that this is, irreducible to Q. This means that equivalently, A squared minus 4B, well, can we say? Right, this is not a square. Because the quadratic formula gives these roots, right? The roots are. And this is rational if and only if this thing is rational. If and only if a squared minus 4b is a rational square, if and only if a squared minus 4b is an integer square, right? Notice that if you have one root, you have the other, right? Because suppose that you take Q, join with A plus the square root of a squared minus 4b over 2, right?
Should be negative then?
What's that?
Negative then?
Yeah. That's right. Notice if you have this root, you have the other. Let's see why. Right, because the sum of the two roots is actually equal to, actually equal to negative A, is it not? That means if you have this one, and if you have this one, you've got that one. Right? So these extensions are normal, right? Here's one with, so I'm gonna bring this example up again because we talked about it earlier.
Is there a particular reason for calling it a normal extension?
Well, I'm not sure about that, the history behind it. Actually, it's gonna turn out these are very closely related to Galois extensions. In fact, this is equivalent to Galois over the rationals, or actually any field characteristic zero. Uh, if you remember this right here, this polynomial here, look at the extension. The roots of this are now notice that in this extension here, this polynomial has a root, right? And therefore, this thing completely splits. Because if you have any one of these four roots, right? If you have any one of these four roots, you have the rest of them. If you have this one, then you have all the rest of them. That's pretty clear. But since all of these are relatively prime to A, notice that if you have this one, then you have its square, which is 9. Then you have this times this, which is, yep, right. So this is relatively prime to 8, so you get everything, right? When you when you square this, you get this to the 6th power. When you cube it, you get this to the 9th power, which is this. So now you've got this 3 powers of this give you this, and so forth. So if you've got any one root of this, then you've got all of them. This is a normal extension. And in fact, every intermediate extension is normal. Yes?
That happens with the root of x to the p minus 1.
Mm-hmm. Yeah, that's right. That's right. And notice,
Good one.
let me do a quick reminder here, what this one looks like. So you have base field Q, and you have Q adjoint this guy. Notice that if you look at the corresponding primes, so this takes us back to the Galois theory. So you get the identity, and these intermediate groups. Notice that the Galois group of this extension is abelian. That means that every intermediate extension is Galois. And we'll see in a moment that means every intermediate extension is normal. Of course, from our previous conversation, you can probably discern this because these are all quadratic extensions of Q, so they have to be. Okay, so can anybody give an example of an extension that's not normal?
Third one, this x to the 3 minus 2.
Boy, that example
I
seems
mean,
to be
that-
very useful, doesn't it? Not normal. Because it's not split. Listen, but notice, we can sort of make it normal in the following sense. This isn't good enough to be normal, but you can expand this field to a slightly larger field, say this one. This one is normal. Over, as it turns out. Basically, how did I do that? I took this polynomial and chucked all the roots in. Now, what may not be clear is, okay, so now I've made it normal with respect to this polynomial. Actually, I've made it normal with respect to every polynomial, as a matter of fact. But we'll get to that. Okay, so we're gonna talk about this a little bit more, but now I'm gonna give you a little teaser here. It turns out the condition that this Galois condition is actually very strong. Galois means normal plus separable. Now, I haven't told you what separable means yet, but we're gonna get to that. But suffice it to say for now, that any field of characteristic zero is separable, right? So for example, if you think about the rationals or the reals or whatever, it's characteristic zero, this is automatic. And so in characteristic zero, Galois and normal are equivalent. Also, is normal. If and only if F is the splitting field, let me just say A now, splitting field for a set of polynomials in KX. So again, so here's what's probably obvious from that. If you have that F is a splitting field of some set of polynomials over K, then certainly F looks like a splitting field for that particular set of polynomials. It's probably not clear at this juncture why this works for all polynomials. That is to say that every polynomial that has a root in F actually splits. But let me give you this theorem here. This was kind of fun. Theorem. Eight point 3.4. Let F be a field. Following conditions are equivalent. A, every non-constant polynomial over F has a root in F. B, every non-constant polynomial f of x splits in f of x. Number C, a non-constant polynomial f of x, and f of x is irreducible if and only if degree of f of x is equal to 1. D, there doesn't exist a non-trivial algebraic extension of that. So F goes as far as you could have gone algebraically. There's a field inside of that such that F is algebraic over K, and every polynomial in K splits. So let's go through this. Okay, so what's easy here?
B plus.
In fact, it plus maybe I could add a word for E. Why does B imply E?
We just choose K to be out.
There you go. Yeah, so if you have that every non-constant polynomial in fx splits in fx, E choose K equals F. That's what I see as kind of the easy ones. So let's do, so B basically implies everything, right? So it doesn't do very good to put B at the front of this. Let's do A. A implies, right, let's do A if and only if B. We'll do A, so then we'll have the equivalence of A and B. Okay, so B implies A, it's clear. How about A implies B? Every polynomial has a root. Let's do this. Suppose f of x and fx Suppose it doesn't split. Then f(x) G1x, the GTX with at least one degree of VI bigger than one. Right? So if it doesn't split, suppose it factors into some product of irreducibles, but at least one of these irreducibles has to be a degree greater than one. Agree?
Doesn't have a root.
Right, so, without loss of generality, suppose, G1 of X is irreducible and degree of G1 of X is bigger than one. But G of X by part A has a root, right? G1 of X has a root lambda in F, then G1 of X is X minus lambda times G1 prime of X. And degree of G1 prime of X greater than one, and this is a contradiction as G1 is not irreducible. So A and B are equivalent. All right. How about C implies B? Okay, so a non-constant polynomial is irreducible if and only if its degree is one. I need to show that every non-constant splits. This is very similar to the previous one. Suppose f of x is G1 GTX with each GIX irreducible. Right? By part C, or by assumption, degree of GIX equals one for all I between 1 and 3. So f of x splits. So now I've got the equivalence of A, B, and C. Right? D is kind of a different one here. Okay, so these three at this point are all equivalent, they're all the same. So let's throw D into the mix. There is no non-trivial algebraic extension of F. So let's do I can use either one of these. They're all equivalent. So there's no non-trivial algebraic extension of F. Let's do it not. Yes.
To make? No, I was thinking the C implies D. Okay, right? Because I was thinking in C implies D.
Yes, yeah, that's right. Well, so we'll do the contrapositive here.
I think A is easiest to show.
Suppose, so I'm gonna hook on the C. suppose there exists f of x and fx
Oh,
that is irreducible. And three of f of x is n bigger than one. So suppose you have a polynomial, suppose you can find a polynomial that is irreducible to degree bigger than one.
then you can algebraic.
Yeah, the strategy is we should be able to construct an algebraic extension, and how do we do that?
With a root of x.
Right. Then, if you look at this is actually more of fx modulo fx and f u over f is a non-trivial algebraic extension of f. So if you've got something that can be reduced, or that can't be reduced and irreducible, you can actually use that to build your algebraic extension. On the other hand, if you want, so how about the other way? Any of these conditions show that there's no non-trivial algebraic extension.
You can assume that you have a algebraic extension of f, but if you have an algebraic extension of f, you have in this extension, or an element that is a root of a polynomial, but then that would have to belong to f.
Okay. Positive again. Suppose that let's say that E is an algebraic, a non-algebraic extension of f.
Wouldn't it be easier to just let K be an algebraic extension and then show that it's F using B?
So like K be an algebraic extension and whatnot.
So like if we let U and K, then we have some polynomial in F since it's algebraic, then we can just use B.
Well, that's what we're doing here, actually, right? Because this algebraic extension is theoretically can be very big. The other thing I know about this algebraic extension E is that everything in it is actually an element that is algebraic over F. And that's the next step here. So select any U that lives in E that is not an F. Right? U is algebraic, which I think is your idea. And
The minimum.
must be root of some irreducible f of x and fx, and the degree of f of x must be bigger than one, since u is not in f. Right? And that's key. And this implies, and so there's what you want. Note f of x is irreducible of in fx of degree And so so not D implies not C. Okay, any questions on that? And so how about, uh, how about, so what we have is A, B, C, D implies E. We've got that already. As B implies E, and now we know these are all equivalent. Check. But E implies that. So what we have is we have some subfield K and F such that F is algebraic, K in every polynomial in KX splits in F of X. So how do we know that every, say, how do we know that every polynomial, I know that every polynomial K of X splits. How do we know that every polynomial? So we know that, of course, our worry is this could be a proper subfield, right? And we know that every polynomial in K of X splits in F of X. How do we know that every polynomial in F of X actually splits? I think it's key here that this is that F is algebraic. Let you be a root. Is a root of F of X in some field extension, right? What do we know about this? Notice that U is algebraic over K. Why is that? Okay, because U, we know that we have K inside F. This is algebraic. And this is algebraic. So in fact, F of U is actually algebraic over K, so in particular, U is algebraic, right, over K. How does that help?
Get a polynomial, okay, and that has to split.
Okay, so let G of X be minimal polynomial for U over K. Okay. Now, what do we know about the relationship between F of X and G of X?
X divides F of X.
I think it's the other way around, right? Because U is actually an F of X. You sort of got more freedom for your coefficients than being over K, right? So So notice, so in particular, G of X, so think of it this way, G of X is in K of X, which is contained in F of X, right? And little f of X is minimal, right? So uh, notice that this polynomial actually splits in F of X, right? Therefore, right, because this is sort of a larger polynomial, right? It has all linear factors. So the same must be true, but this must have all linear factors as well.
Why yes, please?
Hmm?
Why yes, please?
By assumption, because in part E, we said that because G of X is the minimal polynomial for U over K of X. And our assumption in part E is K is the subfield such that every non-constant polynomial over K actually splits in F of X.
We are proving E implies A.
Right, and that's what we're doing. So what happens is no, that is, part E says there is a field K, which is this K here, such that F is algebraic over K, and every polynomial in KX splits in FX.
Okay.
Right? So you know by the fact that G of X is in that small field that it splits there. So, okay, any questions on that? All right, well, we will see you all on Friday.